So we're going to hold back a little bit on what today's work is. The aldol and the Claisen are two named reactions that take small molecules and build them into much, much bigger molecules. We'll do that in a very simple way. And then that will free up time for us to spend a couple of days talking about carbohydrates, which are going to be much more used to you going forward, and a little bit about amino acids, and that would be good. Okay. Anything you need to tell me before we just plow straight ahead and get on with today?
I had a question about the test. Could you hang back after class and I could ask it, or could I ask it now? Okay.
You're talking to me now?
Okay. For the outcome of the multi-step reactions.
Yeah.
I don't remember for one of them I got like a ketone and then you react it with periodic acid, but I don't remember how to do that or if we ever covered that.
Yeah. So if periodic acid is being used in a question that is structured in the way that it sounds like it is for you as a multi-step pathway, that means that the reactant has to be a diol, because periodic acid takes diols and breaks them between those two alcohol groups. And as long as those alcohol groups are not in a fused ring, like a 5-membered ring, where they're both axial but anti to each other, then that bond can break. So
if they're anti, it can't break?
Yeah. So so sometimes, this is a strategy. Sometimes the reagents in the question help you identify what the previous reactant should be. We have no reaction that takes periodic acid and reacts it with anything other than a diol, which means that in a sequence of reactions, if I see the periodic acid here, it means that, to you, the camera, that here has to be a diol. The thing that precedes it has to be a diol.
Okay, because I think for two of them, there's periodic acid where you end up reacting it. For one, I had it reacting with a ketone, but I'm sure that's wrong because it wouldn't make sense. But the other one I have as an anti-diol.
There you go. Now, if it's on a 5-membered ring, those oxygens are too far apart for the poor little per iodate to reach, and it just can't split.
It's on an alkane.
Yeah.
It's not on a ring.
No.
So it doesn't matter.
Then they're allowed that 360 degrees of conformation.
Thank you very much.
Okay.
That helps.
Yeah, and we can do more of that. All right, let's get on. Okay. What we're going to do today are alkylations at the alpha carbon. So we saw last week that if there is a hydrogen and it is in the alpha position to a carbonyl, then though the hydrogens on that position, alpha to the carbonyl, are acidic to the tune of a pKa of about 15 or 16, which is about the same as an alcohol, which is not particularly acidic, but acidic enough to be removed, and be removed fairly easily. And we did 2 reactions on Friday, one that was in acid and managed to remove one of those acidic hydrogens, and one reaction that was in base and managed to remove every hydrogen that is alpha to that position. What we'll do today is remove that hydrogen and then replace it with a carbon, okay? And we'll actually see a mechanism in operation for this. And it's going to start out not particularly difficult. We're going to limit our possibilities. We're going to write a mechanism, and hopefully it makes sense and it looks like it's repeatable. And then over the course of time, we're going to make it more and more and more and more and more complicated, up to the point where if you go back and you read what's in the notes from previous years, that we're going to cut down this year because we're not going to do the full story on the aldol or the full story on the Claisen. You're going to go, well, that's pretty complicated. Okay. Here's an aldehyde. I've chosen an aldehyde because that aldehyde only has alpha hydrogens on one side. Aldehydes can only have alpha hydrogens on one side of the carbonyl because on the other side of the carbonyl there is an aldehyde type hydrogen. Okay. That limits one side of the molecule. It excludes one side of the molecule, which makes our answers easier. Okay. I know that these 2 hydrogens are ever so slightly acidic. So what I'm going to do is I'm going to come and take a base. All right, which base should we use? How many bases do we know?
We can use sodium hydroxide.
Let's give it a try. Let's give the obvious one a try. We might have to come back and change it. Okay, so here's hydroxide. If this is being a base, and both of those alpha hydrogens are being acids, then what's written down, if you've written this down on a page in front of you, you should know where the arrow starts, how the arrow bends, and where the arrow ends. I think fairly obviously it starts at the hydroxide. And it reaches out, and because we've told you it's a base, it reaches out and grabs hold of that hydrogen. The question now is, now what do I do? Because in my starting materials... Go ahead.
Do the electrons go to the carbon?
So I have 2 electrons in this carbon to hydrogen bond, and because I'm taking this with a negative, means I want that to be an H plus that I remove, which means I have no interest in the electrons that are in that carbon-hydrogen bond. And Emily, you want me to shuffle them to here? Okay.
No, directly to the carbon.
Ah, okay. Yes, we can do that. All right, and in fact, let's just do that. This actually gives us an opportunity to talk about, do I want to do this mechanism the easy way? Or do I want to do it the slightly more correct way? When you do it the easy way, and currently what's on the board is the easy way, you identify your base, you identify the acidic hydrogen, you come and take the acidic hydrogen, you don't take any of the electrons from that hydrogen was using in bonding, and you leave them behind on the carbon that the hydrogen was attached to. So now this carbon has a negative charge. That means that that carbon is now a nucleophile. Okay. What we would do in step 2, after we've made, so step 1 is to generate a nucleophile. And then step 2 is to do the actual alkylation. And we generate the nucleophile in base, and we alkylate. I'm going to alkylate by adding a haloalkane. That says Rx. Because if this is a nucleophile, then I know that haloalkanes undergo nucleophilic substitution. They lose the leaving group, and the nucleophile attaches to the carbon. If the nucleophile is a carbon, then I can make a new carbon-carbon bond. So let's make this bromomethane. And in step 2, the nucleophile reaches out. There's an SN2 here. And I still have an aldehyde, but now my aldehyde is branched. It's branched because I just added this methyl. That is the easy, simplistic way of describing this reaction. It is not the most correct. It is, however, the one that if you use, and I will allow you to use this, if you use this methodology of explanation, you are less likely to make mistakes. And so when I'm writing these mechanisms out for myself, mostly I do it the shorthand way. I'm going to call this the shorthand way, because what I can guarantee is that I always know where the nucleophile is. I always know that it's this carbon that's making the new bond. When I write the reaction out the more correct way, it's not always 100% clear where the nucleophile is. So I'm going to allow you to write this mechanism one of two ways. Either the simple way or the more correct way. Here's the more correct way. The base reaches out, grabs hold of the alpha hydrogens, one of them. The two electrons that are making the bond between the carbon and the hydrogen are then put into a double bond. Ooh, that carbon there, that already has 4 bonds. So something has to break. And it breaks out up to the electronegative oxygen. This now has a double bond. There was no double bond up here, not a carbon-to-carbon double bond. This description has a carbon-to-carbon double bond and a negative charge on the oxygen. If that negative charge, if we made it go away by putting a hydrogen on there, this would be an enol. So this is an enol without a hydrogen on it. It's a deprotonated enol. It's called an enolate, and it's still a nucleophile. Alden, go ahead.
For that first easier reaction that you did,
Yeah.
After the last step, would you have a Br minus also?
Oh yeah. Mm-hmm.
Like a negative bromide ion?
Yeah. Okay. This enolate gets to act as a nucleophile. So here is my bromomethane. I've still made water. There it is, floating around. Now what happens is this reforms. I'm going to write it a little bit better than that. And then pushes out the pi bond to reach out to the electrophilic carbon. But we get the same outcome. Okay, so this one is more correct, and we know it's more correct because there's a couple of little silly tests that we can place in the path of the reaction, and in the middle it follows more the rules for what do I want this double bond to be, Zaitse's rule, then it follows the rule for which carbon is the best carbon to put a carbanion on. Okay. So we know that this one is a better description, but this one works and this one is easy. I'm going to allow you to use whichever one you feel the most comfortable with. Okay. And you might not have a most comfortable right now on the first day that you see it, but maybe later. All right, we have to revisit one thing about this mechanism, and it's our choice of base. And if we're revisiting the base, that can only mean one thing. That can mean that hydroxide maybe wasn't the best choice of base. Can anybody posit a reason why hydroxide might not be the best base for this particular reaction? Have a think. Talk amongst yourselves even. Got the pink pen. Go ahead, Matt.
Does it have to do with the strength of the base? Because it's strong.
It is a strong base. What is it other than being strong? What is it also? It's small. With the pink pen, tell me, I haven't done this yet. On the app, see, because my stupid computer wouldn't allow me to use the microphone because the microphone's not working. It means that I have to run this from the app, which means I don't get to get everything that the computer version of this software does. In the computer version, you can poll the audience. Don't get that on the app. Have to make do. So that's why we have to make do with talking to you. With the pink pen, tell me if what I'm about to write is possible. Yes or no? In black ink, the hydroxide is being a base. It reaches out and grabs a hydrogen, which forces a carbanion or enolate nucleophile inside the molecule at the alpha position, and that nucleophile resolves the charge by undergoing a nucleophilic substitution with a haloalkane, and I alkylate at the alpha position. With the pink pen, the hydroxide acts like a nucleophile and undergoes nucleophilic addition at the carbonyl to make a geminal diol. Is what's written down in pink possible? Yes or no?
Yes.
Obviously yes, because we're spending time talking about it. Yes. Ketones and aldehydes react by nucleophilic addition with nucleophiles, and if that nucleophile is a hydroxide, then the product is a geminal diol. I'm going to need another base. I'm going to need a base that is happy being a base but does not want to be a nucleophile. How do I tune a molecule? Think, how do I tune a molecule so that it retains its basicity but gives up its claim to nucleophilicity? What's easier to do? Be a base or be a nucleophile?
Be a base.
It's easier to be a base. The hydrogens that you attack by being a base are always on the outside of the molecule. Being a nucleophile means you have to attach or attack the carbon specific to the reaction that's experiencing electron withdrawal, and it might be in an awkward position. And
do you need something bulky?
Yes. All nucleophiles are bases, but not all bases are nucleophiles. And if we make our base bulky, then it only does the base thing. It doesn't do the nucleophile thing. So I'm going to switch out the base in this reaction. Hydroxide was a good place to start. It turns out that for this particular reaction, that's not going to be the right one. The base that we're going to use is called LDA. And LDA is lithium dibutylamide. LDA, let me see if I can find a place to write it in. Here's a lithium. Lithium's going to be group 1, it's going to be a positive. That means that I can follow it with something that's a negative. Nitrogen, supposed to have 3 bonds. If one of those bonds is has replaced a hydrogen with a group 1, then that leaves me 2 bonds left. And if I make this be a big, I can make this be the isopropyl. So this is lithium diisopropyl amide. This is now a bulky base that is not a nucleophile. So I don't have to worry about it doing the other reaction. I only have to concern myself with it doing the thing that I want it to do. I want it to be a base. I don't want it to be a nucleophile. Okay? Okay. Let's do this again. Let's go ahead, take a molecule that has an alpha hydrogen, make a nucleophile there, and then, remember this, I said this just a minute ago. Things with negative charges could be nucleophiles and could attack the carbon. That's what we're going to do now. We're going to take a molecule. I'm going to turn it into a nucleophile, and then I'm going to have that nucleophile attack another molecule of itself. Okay. The reaction that I'm going to do now is called an aldol. And it's called an aldol because I start with 2 aldehydes, and I make a molecule called an aldol. And in the same way that an enol is part alkene, part alcohol, an aldol is part aldehyde, part alcohol. Technically, the aldehyde is what we call a beta hydroxy, that's an X, aldehyde. This reaction is called an aldol addition. Aldol additions are followed by another reaction that's also called an aldol, that is an aldol condensation. And what an aldol condensation makes is something called an alpha beta unsaturated aldehyde. And it's pretty unlikely that you do the first reaction without also doing the second reaction. It can be done. You can design your reactant to be stable after the first step and only do the addition. But they're probably going to do the condensation. And we can do the addition in base. I'm going to show you the base ones today. I'm not going to show you the acid ones. But the acid ones are exactly the same. So this reaction works whether you do it in base or acid, and the subsequent reaction to it also works whether you do it in base or in acid. And when a reaction works whether you do it in base or acid, means that you have no hope of stopping it. Because if you do the first step in base and then you think, well, I want to stop here now, I'm going to acidify, then the second step just keeps rolling. So we're pretty much going to want to see this go all the way through. Okay, I'm going to give you the simplest version that you can get. This is a carbonyl. It has alpha hydrogens, 3 of them. What's the name of this molecule?
ethanol.
Yeah. This is an aldehyde. So it ends in an al. And there are 2 carbons, so this is ethanal, also known as acetaldehyde. Don't call it acetaldehyde. I'm going to need a base. Here's hydroxide. Now, we just agreed only a couple of minutes ago that if I were to use hydroxide as a base, not only are these alpha hydrogens in play, but also that carbonyl is in play. So I'm going to make this very dilute. It's easy to be a base, easier to be a base than it is to be a nucleophile. So if I pull back on the strength of the base that I'm using, and what I'm doing here is hydroxide's a strong base. So what I'm doing is pulling back on its concentration by making it dilute. Then I leave it the easy reaction. Okay, I'm going to run through this mechanism showing you the enolate variation. If you want to write down the carbanion variation, that's fine. So I'm going to take that hydrogen. I'm going to make the enolate. Now, technically, all of the steps in an aldol can be undone because this is very, very dilute. I'm not really driving this reaction forward. There is a retro aldol that just does everything in reverse. So technically, these are equilibrium errors. If you feel like at this point, I don't want to confuse myself by thinking that this reaction is reversible, although I'm saying it on the record that it is, and you wanted to say, for my own mental health, it's in base, I'm going to have this be an arrow, go ahead. No one's going to call you out on that. Okay? So I've made an enolate. This is my nucleophile. The thing that it's going to react with is a carbonyl, because nucleophiles react with carbonyls by nucleophilic addition. So here's the nucleophile. Actually, I'm going to write that so that here's the electrophile. And here is the enolate nucleophile. All right, put them a little bit further apart from each other. Now that I've written that out the long way, I might just erase it and write it the simple way. So write this down, take a look at it, if you're comfortable with it. If you're saying to yourself at this point, I have already decided I'm going to opt that I don't like this form of the mechanism, I'm going to do it the easier way, with the carbanion. I'm going to redraw this so that you can see it the easy way, because it's only the first step that would be different. Okay, if we went back to that first step, I grab this hydrogen and I put the negative charge on the carbon. What that does for me is, in the next step, I said if you do it the easy way, the simplistic way, you always know where the nucleophile is. Look, the nucleophile's right there. And so now I know where my arrow starts and I know where my arrow finishes. Okay? So to be completely honest, when I'm doing these reactions myself to figure out a problem, most of the time I do it the shorthand way. Most of the time I put a carbanion here, because then I know exactly where the nucleophile is. It's not the most correct way, but it's the way that's least likely to generate an error. Okay. All right, so now I have two carbon fragments and they're going to come together and this could get a little bit ugly. Here's what we do when molecules that have a certain level of mass come together to make a bigger molecule. If I have a molecule over here and a molecule over there, and I know that I have to attach them here by the thumbs, what I don't do is redraw them in some new way. Okay? We've always had the situation where here is a target and then something else has come in and attached. Don't get away from that modality of thinking. Leave this molecule exactly where it is and then have the other molecule come in and dock with it. Okay? Don't try and figure out what the connections are and then rewrite this from scratch. So whatever's going on in the product of this step, I know that's where the reaction went to, right here. It opened up that carbonyl to an alkoxide. There is a methyl. Attached to it. There is also a hydrogen attached to it. And now I'm going to consider this. This big curved arrow is now a bond. So I have a straight line, and what's at the end of that bond, because I did it the simplistic way with the carbanion, is a CH2. And then attached to that is a carbonyl, and it's an aldehyde because there's a hydrogen there. Okay? This is an alkoxide. It's going to reach out and grab hold of the most acidic thing that it can find, and because we're doing this in base, the most acidic thing that it can find is a water. This is the product of the aldol addition. There's an aldehyde. Here's an alcohol. This is part aldehyde, part alcohol. Here's the aldehyde. One position away from the aldehyde is the alpha position. One further position away from the aldehyde is the beta position. So this is a beta hydroxy aldehyde. And whenever you do a mechanism that is an aldehyde, that is an aldol, at this point, check your facts. You should have started with two aldehydes. We can make them be ketones. And at the end of your reaction, if you do not have a beta hydroxy aldehyde or ketone, then what you've done isn't right. Okay, written up in the name here, an aldol is a beta hydroxyaldehyde. Make sure that you have that. Alden, you had a question.
I was curious, that last step that's going to an aldol, is that also possibly in equilibrium, or is that stuff
Oh, yeah.
not?
Yeah, and one of the reasons why it might be possible to see that is we actually generate the hydroxide here again. Okay. Yeah. Okay, so that up to here is our first step. That's the addition. There is something still left to do, and that is the condensation. Here's my product. My product of an aldol addition is alpha, beta, gamma, a beta hydroxy aldehyde. And I still am in base. These hydrogens, alpha hydrogens, are acidic. So let's go take one. If I take that hydrogen, because that's the most acidic thing in the solution, then I'm going to be taking it as H+, which means those electrons that are in the carbon-hydrogen bond here, don't need those. Going to leave those behind. If I do what I'd done previously, and when I remove a hydrogen, I try and make a carbon-carbon double bond out of that, like I did right at the very beginning when I made this an enolate, and then I subsequently erased that and wrote the shorthand version. I'm going to make a carbon-carbon double bond right here. But that carbon already has 4 bonds. So it's going to let go of the weakest thing that it's holding. That gives us a choice of either a carbanion, a hydride ion, or a hydroxide. And it turns out that the hydroxide is the weakest thing that's on that carbon. And as long as the leaving group is not stronger than the base that causes the reaction, then we're okay. We've told you up to this point, the incoming nucleophile, incoming base, has to be a stronger base than the thing that it replaces. Yeah, that's a really good rule. There are times when, right now, there's a kind of a gray area where what's coming in is not stronger than what it's pushing out. But there is an added benefit to the product that makes it happen anyway. These two, the basicity of the thing causing the reaction is the same as the thing leaving the reaction. Okay, now when this leaves, here's what I get. This is an alpha, beta, unsaturated aldehyde. So this last step is the condensation. And again, you can come, because this is not stronger than that, you can come back from this. This first part was the addition, and then we have the condensation. This reaction lets us get around the fact that our incoming agent is not more powerful than the leaving group, because my product is something special. What one word describes what's going on inside the pink blob?
Is it a conjugated pi system?
Well, that's more than one word.
Oh, sorry.
Yeah. My product at the end of all of this is conjugated. And conjugation allows for electron delocalization, which always stabilizes the molecule. So my product of the aldol is lower in energy, sufficiently lower in energy than my reactants to allow this part right here that says you're not strong enough to do this reaction under normal conditions, but I'm going to let you get away with it because I've got something really good here. Okay, that's quite a bit of ground. Here's the deal with the aldol. Don't have to be aldehydes. They can be ketones. And if they're ketones, then I have to decide, do I make the enolate on the left-hand side of the molecule or on the right-hand side of the molecule? Also, they don't have to be the same aldehyde or the same ketone. You can put two different ketones in a flask, add some base, and let them figure out what to make. That gets ugly because there are lots and lots of permutations. When you have two ketones and they each have alpha hydrogens, then that generates more products than you might originally think. That generates lots of products. And then and then a student or a researcher has to figure out, wait a minute, which one of these is the best answer? The other thing that we can do is we can make a molecule that has a carbonyl at this end of the chain and a carbonyl at that end of the chain, turn this one into a nucleophile and have it wrap around on itself and close the loop. So I make a nucleophile here. No, I have more fingers. Make the nucleophile here. That one's waggling. And then make it be the nucleophile to this electrophile and close the ring. So we can cyclize the aldol. It's all in the notes. You won't be tested it over this year. Yay. Because we lost 3-4 days. Okay. Read ahead. There is a follow-up reaction to the aldol called the Claisen, which is actually easier, simpler, cleaner, that instead of using an aldehyde, uses an ester. I'm going to show you 10 minutes of that on Wednesday, and then we're going to hit carbohydrates and basically do biomolecules for the remaining time. Okay? If you want to stick around in the room and ask me questions, go ahead and do that. Otherwise, off to your next class. Have a good day.